permutations and the fundamental counting principles. So the first thing I'm going to say is just very bland, very straightforward. If event 1 has X possible outcomes and event 2 has Y possible outcomes, how many possible outcomes would you have of both of those things occurring? You would multiply X times Y. That's just the general strategy. And it sounds very vague. It sounds very abstract. So right away, we're going to jump into some practical things like talking about this specific idea. Let's say that you are on a soccer team and you have different parts of a uniform to wear. Specifically, your team has 4 shirts that you wear. Let's say there is a blue shirt, a black shirt, a white shirt, and a gray shirt. So any given day, depending on who you're playing, you could wear any one of those colors. So you have 4 shirts. And as part of your uniform, you have 3 pairs of shorts. You have a pair of blue shorts, a pair of white shorts, and a pair of black shorts. So far you could wear blue shirt, blue shorts, blue and white, blue and black, or you could wear black and blue, black and white, black and black, or any of those combinations. So shirts, shorts, and then you have socks. So in some sports, the socks don't matter. If I'm playing basketball, that's not part of my uniform. I could wear whatever I wanted to. But in soccer, the socks are part of the uniform. We all have to wear the same color. So my socks, maybe I have a blue pair, a red pair, and a green pair. Kind of random, like we're just going to say any of these can go together. So the uniforms I could wear blue shirt, blue shorts, and blue socks. That is one uniform. Or I could wear blue shirt, blue socks, or blue shorts and red socks. That is different because not everything is the same. That is a different order. It's called a permutation because the order does matter here. The question is, how many total different uniform combinations or variations could you have? I want you to think about that for a second, and I want you to write down, what is your guess? How many total different uniform combinations can you have? So far, I've gone over 1, 2 possibilities. How many total ones do you think there are?
482.
So maybe it's a really big number. Maybe it's kind of small. Let's see if we can figure this out. To begin with, I'm going to go back to my colors. If I have the blue jersey, I could go blue, blue, blue. I could go blue, blue, red, or I could do blue, 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 green. How many is that so far? 3. Plus, okay, how about I could also do blue, white, blue, blue, white, red, or blue, white, green. How many more is that? 3. Or, sticking with this blue shirt still, I could do blue, black, blue, blue, black, red, or blue, black, green. That was 3 more, wasn't it? So, plus 3 more. And are there any other variations that deal with the blue shirt? Did I get all the blue possibilities out of the way? Agree? Okay. So those are all my blue shirts. Now if I go to the blacks, I could go black, blue, blue, black, blue, red, black, blue, green. How many? Black, white, blue, black, white, red, black, white, green. 3. Black, black, blue, black, black, red, black, black, green. 3. So 3 plus 3 plus 3, 3 plus 3 plus 3. So 9. How many different variations do you think we can get out of the white? How many out of the gray? How many total?
Oh.
Anybody guess 36?
Eric,
Some of you are honest. Some of you are Eric Sheriff. So I did all of the count, or the start of the counting. I got kind of bored. I got kind of lazy. I thought, is there a quicker way to do this? So I didn't draw all the arrows for the white or for the gray. That's using my mind to think smarter, maybe not work harder and all that to get a good strategy. It's not bad to map everything out, especially if I'm stuck. but I want to have a strategy so I don't have to write them down, so I don't have to draw everything either. And this gets into this fundamental counting principle. Here's the thing. How many options do we have for the shirts? 4 times how many options do we have for the shorts? 3 times how many options do we have for the socks? 3. 4 times 3 times 3, 36. That's the idea of this fundamental counting principle. When they are different opportunities, different events, I take the number of these opportunities times those. That will give me all of my possibilities. Fundamental counting principle. Next example. Let's talk about the world of hackers. Hackers, they want to steal your information, right? They try to get your passcode so then they can log into you and make you buy things you don't really want to buy, send them to their address, and you're getting ripped off. So we want to have good passcodes, right? Supercomputers are out there trying to figure out your information all the time. You want to have one that can't be stolen, that can't be guessed easily. So let's look at the number of possibilities for these different passwords. First one. How many different 5-digit passwords are possible? So first digit, second digit, third digit, fourth digit, 5-digit. 5-digit passwords are possible if the first 4 digits must be numbers and the last digit must be a letter, not case sensitive. So for the first one, this has to be a number. How many possibilities are there then for this digit? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0 is a digit. So how many possibilities are there here? 10. 10 possibilities for the first one. Just like here, there were 4 possibilities for our first shirt. How many possibilities are there for the second one? 10. Can we repeat the digit? It doesn't say that we can't. So yeah, sure. How many possibilities for the next one? 10 for the next one. And then the last one is going to be a letter, not case sensitive. In other words, if I type in an A or if I type in an A, it's going to read them the same. So how many letters are there? 26. So what are you going to do? 10 times 10 times 10 times 10 times 26. How many total possibilities are there with this criteria? Now, let's say that our genius hacker in the back of the room decides, I'm going to try to sit down and manually start typing in all these possibilities. How long is it going to take you to type in all 260,000 of these possibilities? A long time, right? Computers, especially supercomputers, can do this really fast. They're not going clunk, 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 clunk. They can get through 260,000 possibilities really fast. So if this is the criteria, that's not a great password. Not a lot of great options. Scrolling down, how many different 6-digit passwords, 1, 2, 3, 4, 5, 6, are possible if the first 4 digits must be numbers and the last 2 are letters? Again, not case sensitive. How many possibilities for the first spot? 10 times. Next one. 10 times. 10 times. Now we're into letters, so times. 26 times 26. Multiply all those up. Are we in the millions? 6 million? Okay. The way I wrote this down is my password would go up on this blank. These are the possibilities. Let's see if any of you can randomly get lucky. I'm going to freeze my screen so those of you sitting here can't see what I'm going to write down. I'm going to write down the password. I want you on the blank. I'm going to change my color as well. Write down the passcode, what you think it is. 4 numbers and then 2 letters. See if anybody gets all 6 of mine. If you do, you won the lottery. That's like 1 in 6 million chance you guess my password. If you guess any of the numbers, letters in the correct spot, that'd still be pretty amazing. Write down what you think the password is. Mm-hmm. Okay, we ready?
Yeah. No.
I have my password down. I got mine down. The first 4 are numbers. The last 2 are letters. Let's see was your first number a 5?
No.
Yes, yes.
Second number a 4?
No.
Third number 2?
No.
Fourth number a 9?
No.
The letters, the first letter A,
No.
the last letter R.
No.
So the probability of anybody getting all 6 of those, 1 in 6.7 million. If you got a couple of those numbers in the right spots, that's still like pretty good, but nobody cracked my code. No hackers in here, at least yet. Okay, next one. How many 5-digit passwords are possible? 1, 2, 3, 4, 5. If the first 3 digits must be letters and the last 2 digits are numbers. This time it says not case sensitive. So A and A are different. So if the first, it says not case sensitive. Oh, I'm sorry, not case sensitive. Yeah. A and A are still the same thing. My bad. I'm getting to the next one already. So how many possibilities for the first one? Next one. Next one. Next one. 10. Before you multiply, this had 6 digits, 6.7 million. This has 5 digits. Are we expecting this to be more or less? Instead of 6, we only have 5, but there's letters, more letters than numbers. So let's see how this one plays out. So with this criteria, you have 1.7 million possibilities. Still a lot. Let's see who's feeling lucky. Here's the criteria. What do you think is my passcode? Good question. So why isn't it bigger? Because when we multiplied the numbers, it was smaller, right? We're thinking, well, 26 is much bigger than 10, so is the other 26 and so forth. But because there's 6 digits on the first one and 5, that made more of a difference rather than the more 26s than the 10s. All right, you ready? Let's see if anybody got my passcode. First letter, A.
No.
R.
No.
S.
No.
1.
No.
4.
No.
Did anybody get 2 or more of those in the right spot? So you can see how hard it can be to get a passcode, to guess one, unless we're like able to do a bunch of guesses, which is what those computers do. Next one, and again, I was getting ahead of myself. Here we are. How many different 6-digit passwords? 1, 2, 3, 4, 5, 6. I don't know if this one is on your notes or not, so let's just squeeze it in at the bottom or on the side. 6-digit passcodes. If the digits can be either numbers or letters, case sensitive. So A is now different than capital A. Really got to think about this. How many possibilities are in this first spot?
62.
So there's 26 lowercase, 26 uppercase, plus it could be a number, right? Like it could be in any order. So 62 possibilities there, yes. The 52 lowercase and uppercase letters plus the 10 digits times how many for the next one? 62, 62, 62, 62, 62. 6 digits, all possible 62s. We're looking at a big number for this one. How many you got, like 9.16 E something?
I got 5.6.
Oops, I only went to the 6th power or the 5th power. Hold on. Back up. So scientific notation, mine came out 5.6800235558 e to the 10th. So what that means is times 10 to the 10th. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 5, 6, 8, 0, 0, 2, 3, 5, 5, 8, 0, comma, comma, comma. If this is the criteria, 6 digits, and each digit could be either a number or a letter, case sensitive, lowercase or uppercase, you have 56,800,000,000 possibilities. All of a sudden, this gets a lot crazier. Much, much bigger number than all the other ones. We went 6 digits before, but we had other criteria on it. This is way more wide open. And so again, I could put any number, any letter, any number, any letter, any number, any letter. A, 1, 2, Z, lowercase r. That would be one of my possibilities. No one's guessing that. Supercomputer going to take a long time. 56 billion possibilities. They're probably not going to be able to hack through all those to get to that. 56 billion, very big number. That's about as much money as like a Jeff Bezos or someone has. Probably a little less than what he has. At one point, Elon Musk was over 100 billion, but he's come back down below that because Tesla has gone down. Okay, so fundamental counting principle. Next page, permutations. All right, use your creative minds, and knowing that my drawing is not up to Sam Bracey's caliber. Here's my drawing. What is it supposed to be right here? Correct, Frankie. This is the inside of a car.
Yay!
Driver, person riding shotgun, behind the driver, and in the worst seat, because you're behind the shotgun, not behind the driver. So there you go. Those are the 4 seats. Frankie is sitting up here. Frankie's got 3 friends that he's going to choose from that are going to sit in this car. Is sitting here different than sitting there or sitting there? Yeah. So maybe he has friend 1, friend 2, friend 3. All of a sudden he realizes they get to a stop sign. No, you said something stupid. Get out of the car. You get demoted, and now you're going to be here. That person's going to be there. So it's a different seating arrangement, right? They get to another one. Person riding shotgun was in charge of the music. Frankie's like, dude, you did a horrible job picking music. You got demoted. Get out of that seat. You're no longer sitting there. You're sitting in the back. So person 1 goes back here. Person 2 goes up there. It's a different seating arrangement. When the order matters, we call these permutations. A permutation is an arrangement into distinguishable different sequences. One is first, one is second, one is third. In the Olympics, is there a difference between first place and second place and third place? Yes, gold, silver, bronze. If you get third instead of second or second instead of third, you get different medals. In other places, maybe the order doesn't matter. To qualify for the Olympics, like in track and field at least, who qualifies? Anybody who gets first, second, or third. So the person who got third place really is no different than the person who got second place. You're not really going for the medals there. You're just trying to qualify. So that case, the order doesn't matter. Whereas when I actually get somewhere and order matters, we talk about permutations. Number of permutations of n elements. Again, it sounds abstract. Permutation, element, what is this? What is the n factorial? If I have 5 different things that I want to put in a certain order, there are 5 exclamation point possibilities for that. This exclamation point is called factorial. The n with this exclamation point doesn't mean n. It doesn't mean like exclaim, like more exciting for. That's not like a punctuation. It is actually a symbol like add, subtract, multiply, divide. It means something specific. For example, if I had 5 factorial, what that means is 1 times 2 times 3 times 4 times 5. That's what it means. My calculator can do this. On the graphing calculator, if I hit 5, so some of you I know have the graphing calculator. If I hit 5, how do I bring up that exclamation point? I'll go to math, scroll to the right where it says probability. I'll scroll down to number 4, hit equals. There's my 5 factorial. And in the calculator, it's doing 1 times 2 times 3 times 4 times 5. Now, not everybody has the graphing calculator. So on the scientific calculator, if I want that to happen, I'm going to hit the number 5. Then near the top in the second row, do you see where it says PRB? So there's an LOG, then a PRB. So hit 5, hit PRB, scroll to the right to where it has the exclamation point. So it brings up 5 exclamation point, hit equals. It should come out to 120. The calculator knows it's taking 1 times 2 times 3 times 4 times 5. That is the factorial. Okay, so that is factorial. Getting back to more concrete, and the factorial is going to come back to this. Question, how many ways can you order the letters A, B, C, D?
16. What?
A, B, C, D. There's 1, right? A is first, B is second, C is third, D is fourth. How about A, B, D, C? That's different, right?
Yeah.
Do we have any more orders where A is first, B is second? A, B, C, D, A, B, D, C. How about now we go A, C, B, D? Are there any other ways where A is first and C is second? A is first, C is second. What else could be? A, C, D, B, right? Are there any other ways where A is first and C is second?
Guys, it's not 16. D.
So it could be A, D, B, C. Are there any other A's first? A, D, C, B. Are there any other A's? No. So this is the start of a list. A is first. How many possibilities do we have so far? How many?
24.
Right now, how many do we have?
Oh, wait. Right now, bro.
6, right? There's 6.
Sorry.
A, there's no more that have A first, but couldn't B be first? How many B's do you think there are?
6.
I want you to try to list them. We're not going to do every single possibility, but I want you to see what's going on here. Can you list all of the B's? For instance, BA, CD, BA, DC. Can you list all the B's? How about BCDA, BCAD, or BDAC, BDCA? Those are all my B possibilities. So if there's 6 ways that A can lead off, 6 ways that B can lead off, then how many C would there be? 6. How many D's would there be? 6. So 6 plus 6 plus 6 plus 6 is like 6 times 4. 24 possibilities. Again, I could actually list all of them. 24 isn't a horrible thing to have to write down 24 different variations of them. But after a while, again, I'm looking at patterns and trying to figure out, what do I notice? Can I make this a little bit shorter for myself? So yeah, 24. Is there a way I can do this without having to write any of them? And the answer to that is yes. 1, 2, 3, 4. Just like we did with the passwords, there's 4 different spots. Agree? When we start all of this, how many possibilities are there for the first slot?
There's,
4, right? It could be the A, the B, the C, or the D. Once that's chosen, then how many possibilities are there for the second spot? 3. If we already used the A, then there's only B, C, and D left. Once the first spot is chosen and the second spot is chosen, how many possibilities are left for the third spot? 2. And then how many is left for the last spot? Just the 1. This is our fundamental counting principle again. 4 times 3 times 2 times 1. There's your 24. This is a permutation with the order mattering. Up above, that's what this is showing. If I have 4 different elements or 4 different letters, and I want to order them and all the possibilities, I would do 4 factorial, which is the same thing as 1 times 2 times 3 times 4. On my calculator, 4 math factorial equals, there's my 24. I don't want to always have to list things out if I don't have to. Example, 6-digit password again. Numbers cannot be repeated. We can only use numbers. So 1, 2, 3, 4, 5, 6. How many possibilities are there for this first spot? We're just using
6, 5, 4, 3,
Oh, yeah.
1.
just using numbers.
Wait, no. 10, 9, 8, 7, 6. What?
Should start with that.
So how many possibilities are here?
10.
10.
9.
Then, and I'll put this below because this isn't the actual password. So there's 10 possibilities. Now, whatever number we chose here cannot be repeated on the next one. So how many possibilities are here?
9.
9. Once those first 2 digits have been chosen, how many are possible here?
8.
8, 7, 6, 5. So it's not 6 factorial. I don't have 6 choices, right? There weren't 6 letters that I'm picking from. There were actually 10, and then there's 9, and then there's 8. So here's my fundamental counting principle again. I can't just randomly say 6 factorial because I see a 6. I have to think about the scenario. 10 possibilities times 9 times 8 times 7 times 6 times 5. Multiply that up. This is how many possibilities we have. Total of 151,200 possibilities. Not a huge number, but still, if I put down some secret code, the chance that any of you here guess it on your first try or any tries that did it a bunch of times, probably not going to get it.
Let's do it right now.
Make a guess. Write down your answer in the blank.
Wait, I was just have only 5 numbers? Or I thought
6 digits.
oh, 6. Okay.
First, the second, the third, the fourth, the fifth, the sixth. So drawing this out, I think, is how I knew I came up with these numbers, 10 all the way down to 5. If I didn't draw that, would I have known I need to go all the way to 5? Not necessarily. Okay, you ready? I'm going to put mine up here. These all are going to be digits, and you cannot repeat. So if you put a 7 in the first spot, you can't put a 7 after that. Okay, we ready?
1 to 1.
Did you guess my number? You had a 1 in 151,200 chance of getting it.
I got 1 number correct.
So far, we all failed. Okay, cross yours off. I'll give you one more chance. I'm going to guess a different code. So now you get a second chance at this one. Are we ready? Do we have any winners? 843-250.
I have 8.
So we can do this for a long time. Since there's so many possibilities, it's likely that none of you are ever going to guess mine. Unless I gave you a ton of guesses and I didn't change mine, then eventually you might get there. It's going to take a very, very long time. Okay, let's say that you have a minivan.
Where is this?
Just talking. Let's say you have a minivan, and there's 6 of you, and each person is just as likely to be in any of the spots. So this is Holden's minivan, his Kia minivan. He's a nice guy. You ride with him. He might let you drive or not. How many different possible seating arrangements are there? You think there's only 6 people. Surely there's that many combinations. But in how many different ways can these 6 people sit in these 6 spots? How many people can sit in this driver's location? Assuming everyone can sit, there's 6 possibilities to begin with, right? Any one of those 6 people. But once we have the driver established, then how many people are left to ride shotgun? 5. How about to ride here? Here. Here. And then you get stuck in the back corner. What do we do with these numbers? Multiply them. 6 times 5 times 4 times 3 times 2 times 1. That's a few buttons to push, right? But isn't that the same thing as 6 factorial? 1 times 2 times 3 times 4 times 5 times 6. So 6 exclamation point, 6 factorial. It might seem strange, but there are 720 different possible seating arrangements with only these 6 people and those 6 seats. Do I want to draw out, label all 720 of these seating arrangements? No way. So that's why being able to calculate them is going to be such a big advantage for us. Okay, next. What if we don't take everybody? So let's say Holden has 10 friends, and of those 10 friends, we have 6 spots for them in the car. If they sit in different spots, then that's a different seating arrangement. That's a different scenario because that's going to give us more. That is this NPR. So what we would say for this is, out of his 10 friends, in how many ways can we pick 6 where the order matters? The word permutation starts with P. The word order starts with O. They're right next to each other alphabetically. When order matters, we want a permutation. Because we're eventually going to get to what are called combinations, and that's when order doesn't matter. Maybe we'll get that today, maybe we'll get to that on Monday. But if the order matters, if driving is different than sitting in the shotgun seat, is different than sitting in the second row, then the order matters. Sometimes order matters. Gold is different than silver and bronze. First, second, and third are different. Versus, if we're all sitting in this classroom and I'm just going to find a seat for everyone, well, then maybe that doesn't matter because at least you're in the room, right? I want to go to a Taylor Swift concert. I don't really care where I sit and how many ways can I get into that concert. Well, I'm just in there, so that's all that matters, as opposed to I need to sit in this location next to that person. Then the order would matter. This formula, NPR, looks like this. We have those factorials again. And by hand, it looks like the numerator divided by n minus r in the denominator. We're going to do a couple examples by hand so you can see what happens if you have really big numbers and the calculator can't comprehend it. That happens sometimes. Sometimes the calculator gets what's called an overflow error because it's just the numbers are too big to comprehend. But we can do them by hand. They're not that bad. Example, 9p3 using this. It's going to be a fraction, and the numerator is supposed to be this number out front, 9 factorial. So I'm going to write all those out. That's what the numerator looks like. The denominator is supposed to be n minus r factorial, or in our case, 9 minus 3 is 6, so it's 6 factorial. 1 times 2 times 3 times 4 times 5 times 6. And maybe you're looking at this saying, are you kidding? I'm supposed to do this by hand? I'm supposed to multiply all of these numbers, and take this huge number divided by that huge number? That's the idea. And part of that makes it maybe so difficult for you is like, I'm then supposed to divide those, but the dividing by part is what actually makes this doable. It's what actually makes this a lot easier. Because what I know about dividing fractions is that whatever I divide the numerator by, I'm also going to divide the denominator by. So what if I divide the numerator and denominator both by 1? Then those are gone. I can divide the numerator and denominator both by 2, 3, 4, 5. I can divide the numerator and denominator by 6. And look at that. My entire denominator is gone. Great. The only thing that's left is the numerator, 7 times 8 times 9. Now, I know that 7 times 8 is 56. I need to multiply that by another 9. 6 times 9 is 54. 9 times 5 is 45. 45 plus 5 is 50. So this comes out to 504. I know I did that kind of quickly. I'm good with multiplying numbers maybe, but I only had to do a 2-digit number times a 1-digit number. I can do that one by hand. It wasn't too bad. The second one as well, by hand, isn't too bad. So NPR, it's the first number factorial over n minus r factorial. The numerator, 1 times 2 times 3, all the way up to 10. There's no way I'm multiplying all those out on my own by hand. That's going to be a huge number. I know that's going to be a huge number. But in the denominator, n minus r, so 10 minus 2 is 8. We're going 1 to 8. And that's the saving part of this one, because as I'm looking to simplify, gone, 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 canceled, simplified. Almost everything is gone. My entire denominator is gone. All that's left in the numerator is 9 times 10, and I know that's 90. So by hand, sometimes just isn't that bad. I don't really like writing out all those numbers, but if I have something that's too big to put onto the calculator, and that happens sometimes, I can think about like what's going to cancel out and what's going to be left. Fortunately, though, the calculator can do these. 12p8. So on my calculator, I'm going to hit 12. Those of you with the scientific calculator, hit that same button you hit before. And you want to choose where it says NPR. So I have 12p8 on mine. If you have the scientific, you typed in 12. You choose the NPR, then 8, hit equals, and it gives us this rather large number. $19,958,400. There's no way I'm doing that one by hand. And it's not too big, so my calculator can do it. What this means is, if you have 12 items, in how many ways can you pick 8 where the order matters? And there's a lot, 19 million ways you can make that happen. For the next one, do 3p5. This is kind of a weird case. It doesn't give you an error, but when you do 3p5, what did it come out to? 0. So here's the scenario there. Why did it give me a 0? Well, in how many ways out of 3 items can you pick 5? So I'm giving you 3 choices. In how many ways can you pick 5 of them? It's an impossible scenario, isn't it? Like, out of 3 things, I can't pick 5. There's not 5 to choose from. So there's 0 possible ways to make it happen. The first number always has to be greater than or equal to the last number. If it was 5p5, in how many ways from these 5 could you pick 5? Just 1. And if the first number is bigger, I start getting more choices. But if the first number is smaller, it's always going to be a 0. I can use my calculator to verify that. So know how to calculate these on the calculator. More important, know how to apply this in context. Anybody in track? Cross country? Running in general? Solamente señora? So there are 6 people running. Person A, B, C, D, E, F. Albert, Beulah, Christopher, Declan, Edward, Frankie. These 6 people are running. They're running a race they want to win. Is first place different than second place, different than third place? Yes. Like, here's one possible way they could finish. Or it could be A, B, C, D, F, E. Frankie got a little faster. And the third race, he really woke up. Third race, Frankie, Albert, Beulah, Christopher, Declan, Edward. That's different than all the other ones, right? The order's starting to change. There's a lot of ways I could rearrange these, getting, really, all I care about, though, is first, second, and third. I don't care who's getting 4th. I don't care who's getting 5th. I don't care who's getting 6th. Gold medal, silver medal, bronze medal. I don't care about those. All I care about is this. How do I do a problem like this? 6 people. And how many ways can we pick 3? Out of the 6, in how many ways can we order just the top 3? Not the top 6, not the top 4, just the top 3. So calculator, 6, math, NPR, 3. There are 120 possible ways to get a first, a different second, a different third. One more example. That's when I care about first, second, and third. Sorry, you losers in fourth, fifth, and sixth. I didn't care in that scenario. I only cared about the gold, silver, and bronze. The next scenario, there are 6 people running the race. Albert, Beulah, Christopher, Declan, Edward, and Frankie. Now I care about the 4th place and the 5th place and the 6th place. How many people are we picking from?
6.
And how many places do we care about? 6p6. Use your calculator. What is 6p6? I'm expecting this to be bigger because all of a sudden now 4th place and 5th place and 6th place matter. Going back up to my earlier example, these 2 results, even though Frankie and Edward were in different spots, these 2 results for first, second, and third are really the same. So that one wouldn't have even counted, even though the 4th, 5th, and 6th changed. But now for this one, A, B, C, D, E, F is different than A, B, C, D, F, E because I care about 5th and 6th place. Before I didn't care about slow Frankie. Now I'm saying slow Frankie matters. 5th is different than 6th because we care about all 6 of those places. Gold, silver, bronze is one thing, but if you were in track, you do get some points for your team for 4th place and 5th place and 6th place. It is something, so we do care about that. You might not get the medal or the ribbon, but it still is points, so all of a sudden we do care. So these are counting principles. Permutation when order matters, and we'll go further eventually into combinations where order doesn't matter. So just scrolling down a little bit, like this is not a one-day section. We'll continue this on Monday. Reminder, Tuesday we have our stem and leaf, the last section. Wednesday, Thursday review. Next Friday is our test.